Hello guys, welcome to the live session of NPTEL course Principles of Casting Technology week 4 taught by Professor PK Jha. My name is Ganesh Shankar Bhandari and I am a PMRF research fellow in IIT Roorkee. So we will wait for 5-10 more minutes. We will see if anyone joins. Uh, After that we will start. Okay, so we will start with the session. And as you have read in your fourth week lectures, uh, you have read about rising risers. You have read about how to design a riser for the perfect casting to avoid liquid shrinkage and solidification shrinkage. So there are three types, three methods. First is Keynes method, then modulus method, or and NRL method for designing a perfect riser so that it can solidify after your so after the solidification of your casting to provide you with a perfect casting without defects. So first is Keynes method. In Keynes method, what we see, there is a formula for a perfect riser design for calculating the diameter and height of the riser. So that equation is x equal to a upon by minus b plus c. So here a, b, and c are the depends on your different materials, and they are your material properties. And bi is basically volume of riser upon volume of casting. Then X is defined as your freezing ratio, that is VRAR, volume of riser upon area of riser upon volume of casting divided by area of casting. So that will be the freezing ratio. So here we can see a relation between volume of riser to volume of casting to the freezing ratio. So for a sound casting, we have there is a line. So your if your freezing ratio is around, from this graph we can consider if your freezing ratio is 1.5, so your to uh, volume of riser to volume of casting should be around 0.35 or 0.3. So you get a sound casting and your riser does not solidify before your casting. Then coming to the second method, we have modulus method. In modulus method, what we generally consider the modulus of the casting. So that will be the volume upon surface area of casting. So to avoid shrinkage defect, modulus of riser should be more than modulus of casting. So MR equal to 1.2 MC. That is the rule in during designing in by modulus method. So when we are considering a typical cylindrical riser with d equal to h with diameter and height equal, so mr will become pi by 4 d square into d, that will be the volume of your casting, and your volume of riser will be pi by 4 d cube, and volume of and area of riser will be pi d square plus pi by 4 d square. So that will be that will come around d by 5. And when we consider about modulus to surface area ratio of casting, so that will be around uh, mr equal to 1.2 mc. So if when we are going to calculate the modulus of our casting design, so that in the after solving we will get a value of d equal to 6 mc. So diameter of your riser will be typically equal to 6 into modulus of casting. Coming to the next method, which is known as NRL or safe factor method. NRL is basically stands for Naval Research Laboratory USA. This factor is named as NRL or safe factor method because it was developed by the Naval Research Laboratory US. In NRL method, we can say this is it's a very simplified method to the Keynes method. In Keynes method, we have to consider A, B, C. Sometimes if we are not if we do not know the ABC constant of a particular material, then we will not be able to design a riser with the help of Keynes method. So the Naval Research Laboratory has simplified this Keynes method, and they have provided their own method named as NRL or safe factor method. In NRL method, what we consider freezing ratio term in Keynes method. In term safe factor method, we have replaced this term by the safe factor method. And safe factor is ratio is defined basically as L plus W by T. So L will be the length of casting, W will be the width of casting, and T is thickness of casting, where L, W, and T are calculated based on the maximum dimension of the parent section of casting. We are not talking about the parts which are appendices which are joined with your casting. We are talking about maximum dimensions of the parent section of casting. So here from with the help of those factors we can calculate L plus W by T. If casting has appendages, they are also considering towards calculating total riser volume required to feed parents as well as appendage volume. So the factors will change and there are some formulas which we can use for the appendage. Uh, Coming to the graph, so as we can see with the help of this graph we can calculate our safe factor. So VR by VC equal to L plus W by T. When we are going to calculate the safe factor L plus W by T, and we are going to calculate the volume of riser with divided by volume of casting. So when we are going to compare with these, uh, the we are going to take the values from this graph for designing a perfect riser. So if the L plus W by T equal to 16 and VR by VC ratio is around 0. So according to sound casting relation, the volume of riser to volume of casting will be around something 0.37. So if we know the volume of our casting, so we can easily calculate the volume of riser. So that will become VR equal to 0.37 times of volume of casting. So with the help of the safe factor and with this graph we can easily calculate the volume of riser, and after calculating the volume of riser we can calculate the dimensions of the riser. Coming to next thing, when we talk about appendage in the appendage in the risers system, in the casting system, so appendage may be classified as plates and bars, and the percentage of parastic volume will be depend on how we are feeding that. If we are feeding a bar feeding plate, so if we are feeding a plate from a bar system, so the appendage will go like this and thickness so we can calculate our VR by VC ratio from this. So what we have to do if we are going with this thickness around 0.4 and we are considering the bar feeding plate area, so we have to just add around 65% of your casting ball 65% of total volume of your parent volume to your casting volume. So that will be the uh, that we will consider as the volume of your appendage. So so if the volume of casting is 1 meter cube, then you have to add 0.65 meter cube in your casting volume, and that will be going to be your final casting volume. And if we consider the last problem, so here there we have calculated volume of riser equal to volume of 0.35 volume of casting. So now the new volume of riser will be 0.35 into volume of casting. You have to consider this 1 plus 0.65 meter cube volume of casting. So that will the volume of riser will get changed. Now coming to the questions related to the riser methods. So, first question is the main requisites of an effective riser are it must have sufficient volume as it should be the first part of the casting to freeze. It must completely cover the sectional thickness that requires feeding. It should be so designed that it establishes and affects temperature gradients within the casting so that the furthest section directionally towards the riser. So, we will go one by one point. It must have sufficient volume as it should be the first of the casting to get freeze. I think this should not be correct one because the riser should be the last one to last part should be freeze in your casting method so that it can provide it can continuously provide the liquid to your metal casting during to avoid liquefaction. Someone wants to join. So first one will be the incorrect one. It must completely cover the sectional thickness that requires feeding. This is correct. It should be so designed that it establishes affects temperature gradients within the casting, so that you can get directional solidification directly towards the riser. So that is also correct one. So answer should be D, second and third only. Coming to next question. Refer the given solidification curve. Contraction occur during A to B, uh, from this part to this part, then B to C, from here to here, and C to D are known as. So any answer for that? So when we talk about our solidification curve, we talk about three portions. So that will be your uh, solidification starting point, and that is known as liquid. So in this section, you will get your liquid shrinkage, and in this section from here to here, your solidification has already started. So you will get solid contraction. Solidification contraction will be there. Whatever the during solidification, that is going to contract, and the last one will be your solid contraction, because the liquid material has already solidified. After that, the changes will occur due to your solid contraction. So the answer will be liquid contraction, then from A to B, that will be A to B, B to C, and C to D. So the answer will be this one. So coming to next question. Refer the given solidification curve. Which part of the contraction in the curve is compensated by riser? So when we talk about the riser, we talk about liquefaction shrinkage and solidification shrinkage. So here we can consider the riser feeding, because liquid is going to shrink. So you can pass on liquid metal from your riser to avoid this shrinkage. Then here we are talking about solidification shrinkage. Here we can also uh, also avoid it with the help of riser. So the answer will be AB and BC only. And here the shrinkage will be after your solidification. So this type of shrinkage you have to avoid with the help of your pattern. You have to provide some allowances in your pattern, so that you can get a perfect casting by avoiding this shrinkage. Coming to next question. Which part of the contraction in the curve is compensated by providing shrinkage allowance? So as we have talked about, we have to provide solidification shrinkage. We have to provide shrinkage allowances to allow to nullify this solid shrinkage. So the answer will be C, D only. Coming to next question. So we have a numerical here, a cubic casting of 50 mm side. Okay, so we can easily calculate the volume of our cubic casting. 50 mm side undergoes volumetric solidification shrinkage and volumetric solid contraction of 4% and 6%. So we are talking about two shrinkage here. We are talking about solidification shrinkage and another is solid contraction. So that is respectively 4% and 6%. So and we are talking about no riser is used. Assume uniform cooling in all directions. The side of the cube after solidification and contraction is. So we have to calculate, this is our pattern area. This is going to be the, this is what we have used, pattern volume, and we have to calculate the final casting volume and the dimensions of casting. So try to solve it. Okay. Someone wants to join. Hello Randy. So we are trying to solve this question. So please have a look at it and try to solve it. We will discuss it after 2-3 minutes. First try to solve it. Okay, so now we will try to solve this question. As we can see, we are talking about two types of volumetric shrinkage. First is solidification shrinkage and then is solid contraction of 4% and 6%. So your volume of casting will be around 50, can be calculated as 50 into 50 into 50. So that will be your what you are filling in your casting cavity, but you have to take in account the shrinkage. also. So we have two shrinkage here. We have first is 4% shrinkage. So 4 upon 100 into, then second is 6%. So the final volume of the casting, whatever you are going to get, will be according to this one. So we can calculate this. Okay, I think sorry. This will be 9 because you are going to calculate the account for shrinkage, so that will be 96 and 0.94. So that is going to be your 50 into 50 into 50 to 96 into 94 divided by 100 divided by 100. So that is coming around 112800 mm cube. Okay, so after that you can easily calculate your considering it is cubic casting, so your one side will be 1880 cube root. Okay, so your answer will be 48.317 mm. So approximately it will be 48.32 mm. Okay, so when we are talking about no riser is used, so we can just consider the volumetric contraction and solidification contraction, and we can easily calculate the final casting of the casting volume whichever we are going to get. So coming to next question. A cast steel slab of dimension 30 into 20 into 5 centimeter is poured horizontally using a side riser. We are talking about a side riser. The riser is cylindrical in shape with diameter and height both equal to d. So the condition is given h equal to d, and we can consider it as d. Top as well as bottom face of the riser contribute towards heat loss. The freezing ratio of the mold is, so what we have to calculate, we have to calculate the freezing ratio of the mold. So try to solve it. We will be back after 2 minutes. You have 2 minutes time. You can try to solve it. Okay, so coming to freezing ratio, we have to calculate the freezing ratio of the mold. So freezing ratio is defined as uh, surface area upon volume upon casting upon divided by surface area to volume of your riser. So considering that we have a steel slab of dimension this, so we can easily calculate the surface area to volume ratio of casting 30 into 20 into 5 upon. So we have, okay, so 2 into plus 2 into, and for riser we have given a condition that h equal to d, height is equal to your diameter. So we can calculate the surface area as pi d square, pi by 4d square plus that will be, yeah, pi by 4d square into d and pi r square h. So that will be pi d square into divided by the volume of casting, pi d cube. So after solving it, we will get a value of around 8d by 75. So answer is A. Coming to next question. The shape factor of a casting in the form of an annular cylinder of outside diameter 30, inside diameter 20 centimeter and height 30 centimeter, and correction factor is given k equal to 1 will be. So we have to calculate the shape factor and we know the formula. Shape factor is L plus W divided by T, and correction factor is given as 1. So first we will draw a drawing for this casting. So it will look like this. So height is 30 centimeter. Then we have a internal diameter of 20 centimeter. We have a external diameter of 30 centimeter. So we have to calculate the shape factor. Try to solve it. Then we will discuss it. Okay, so we have to calculate the shape factor, that is the formula for shape factor L plus W by T. So length here will be, we have the length as 30 centimeter. Then we have to calculate the width. So considering it as a hollow sphere, so we have to calculate the length according to the that width will be annular width. So this will become 30 plus 20 divided by 2 into pi. So shape factor will become your length 30 centimeter plus 25 by 25 pi divided by your this thickness is 5 5 centimeter. So shape factor will come as 25 into 3.14 plus 30 divided by 5. So it is coming 21.7. So the answer will be around 21.77. Okay. So coming to next question. In sand casting, fluidity of the molten metal increases with. So if we are going, so we will consider all options one by one. Increase in degree of superheat. I think yes, if we are going to increase the degree of superheat, that will increase the fluidity of your molten metal into a sand casting. Then decrease in pouring rate. I don't think so, because if you are going to decrease your pouring rate, then uh, metal will come into the surroundings, and it will start to solidify as soon as you are going to pour it into your sand casting. So it will decrease your fluidity of molten metal. Increase in thermal conductivity of the mold, that will not going to help, because if you are going to increase the thermal conductivity of the mold, so your solidification rate will be very much higher. So you are going to so the molten metal will going to get solidify early, and you will not get any fluidity of molten metal into your sand casting. Then increase in sand grain size, that will not affect your fluidity. So answer is increase in degree of superheat. By increasing the degree of superheat, you can increase the fluidity of molten metal. If we talk about superheat, so that is like if your molten metal melting temperature of a alloy or whatever the metal you are going to melt is around 1400 degrees Celsius. So before going for pouring it in a sand casting, you have to provide some superheat. It's like you have to go with 1600 degrees Celsius, or you can go with around 1700 degrees Celsius of temperature for that molten metal. So the difference between the melting temperature and at what temperature you are going to pour it in your sand casting, that is known as the superheat of your molten metal. So the increase in degree of superheat will result in the increased fluidity of molten metal in your sand casting. Coming to next question, which of the following statement is correct? Chills increases cooling rate in casting. Chill increases the center line feeding resistance. So when first we will talk about chills. What is chills? So when we talk about some casting, bigger casting like this, so what you will get, the solidification rate will be higher here. Solidification rate will be much higher here, but here the solidification rate will be lower due to the divergence problem, due to the conduction. So here we will provide some chills, so that the solidification rate here and here will be the same. So that will increase the cooling, or if we are going to provide the chills here, so that it what it will do, it will increase the heat conduction rate of your casting. So the molten metal will be solidifying earlier. So chills increases cooling rate in casting. Yes. Chills increases the center line feeding resistance. No, this is not true because chills has no effect on your center line feeding resistance. That is basically the property of your material, whatever you are going to pour it in your casting. So chills will not improve the center line feeding resistance in any case. So the answer will be first only. Coming to next question. So we have one more numerical here. Determine the dimension of an optimum cylindrical riser. Height equal to diameter. We have given a condition h equal to d for riser. Attached to the side of a steel plate casting having dimension 25 by 12.5 by 5 centimeter. So we have to calculate the dimension of an optimum cylindrical riser by using Keynes method, by using modulus method, and by using shape factor method. So considering, so try to solve it. We will discuss it after 2-3 minutes. Okay. So now we will first try to solve it with the help of Keynes method. So as we know, Keynes method, A upon by minus B plus C. So here we have A, we have B, and we have C values here. what we have to calculate, we first we have to calculate the x and y value, so that we can create a equation for d, and we can calculate the uh, d value. So x is defined as the area upon volume of your casting divided by area upon volume of your riser. So we know here h equal to d. In the case of riser, the condition is given, so we can calculate uh, the area to volume ratio of casting easily here, and we can calculate the area to volume ratio of riser here. So that will give us some value of x and y, and after putting those values in x and values of x or y in this equations, we can calculate the d value. So it will come around d equal to, after solving it, 11.44 centimeter, or we can say approximate 12 centimeter. And as we know, we have the condition h equal to d. So for riser, we can design diameter will be 12 centimeter and height will be 12 centimeter. Now coming, so first one is okay. We can directly put it in the formula. We have all equations here. Uh, then coming to modulus method. In Someone is asking something. Okay. So coming to next method, our next is our modulus method. So in case of modulus method, what we consider, we know that modulus of casting is defined as volume of casting divided by area of casting. And we know one thing, that your riser, modulus of riser should be 1.2 times of modulus of casting, so that your riser solidify later compared to your casting. So when we are going to calculate this modulus of casting VC by AC, so that will be 31. Volume of casting is 3125 centimeter cube according to these dimensions, and area of casting is 1750. So it will come around 1.785. Okay, so according to our AMR, uh, so we have a condition here h equal to d. So when we are going to calculate the modulus of riser, volume of riser upon area of riser, so it will come around 0.2d. And as we know, uh, earlier we have calculated d equal to 6 mc for riser having height or diameter equal. So we can directly put the modulus of casting to calculate the diameter, or we can go with the MR value should be, MR has to be 1.2 of modulus of casting. You can go
Hello,
with
sir.
that way also.
Your voice
Yeah,
is not right.
voice is not coming. Repeat. Am I audible now? Hello.
Your voice not audible.
Voice is not audible. Now it is okay. 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 Now it is audible.
Yes, sir. It is audible.
Okay. Okay. I think the microphone was not on. Okay. So we can calculate the modulus of we can easily calculate the riser volume according to our modulus method with the help of this formula. Modulus of casting is equal to volume of casting upon area of casting. Similarly, we can calculate the modulus of riser also, and we know that the modulus of riser should be 1.2 times of modulus of casting to design a riser so that it can solidify later compared to your casting. So what we have calculated the volume of casting 3125 centimeter cube, area of casting as 1750 centimeter cube. That ratio will come around 1.7857 centimeter. Similarly, we can calculate the modulus of riser with this with the help of this condition H equal to D. And earlier we have seen that if H equal to D, the height of riser is equal to the diameter of your riser. So the diameter of riser will be equal to 6 into modulus of your casting. So you can easily calculate the diameter of your riser, and as you know, height is equal to diameter, so you can design a riser according to that. Now coming to the safe factor method. Okay, so coming to safe factor method. So in safe factor method, what we have learned that safe factor is equal to L plus W divided by T. So these will be the maximum dimensions of your casting. So the casting which we have got, we have L as 25 centimeter. We have a width of 12.5 centimeter, and we have a thickness of 5 centimeter. So we can calculate the safe factor according to this. So safe factor will come around 10. And one thing more we have to calculate. We have to calculate VC, volume of casting, that was 3.25 centimeter cube, and area of casting was uh, 1750 centimeter square. So we can calculate the, and one more thing we have to consider in case of safe factor method. We have to consider this graph to calculate the VR by VC ratio. So we have our safe factor L plus W by T we have calculated as 10. So that will come into around this range if we consider this graph. So we have the value of safe factor. We can interpolate our line according to this, and we can calculate the value of this VR by VC. So in our case, that VR by VC value is coming at around volume of riser to volume of casting value is coming around 0.47. So with the help of this, we can calculate, we have the volume of casting. So we are equal to 0.47 into 3125 centimeter cube. Okay. So we have the volume of riser, and we know that riser is a cylindrical cylinder and having dimensions h equal to d. So we can calculate the diameter of the riser with the help of this shape factor method. Next, what we have got next, we have got in the same question, assume that the volumetric shrinkage of solidification is 3% for steel and that the volume of riser is 3 times by shrinkage consideration alone. So according to that consideration we have to calculate the riser volume. So what we have got here, we have got the volume of riser equal to 0.03 times of volume of casting into 3 times. So that will be going to be the volume of our riser. So according to that we can calculate the H and D. And one thing you can observe, by all methods most of the time you are going to get around approximate similar values but not the same values. There will be some difference in the values of your H and D. So according to modulus method you will get a value of around, you have got a value of around 11 centimeter for D, and according to your NLR, according to Keynes method you have got a value of around 11.44 centimeter. For modulus method you have got a value of 11 centimeter. So there will be a slight difference in these values. So according to that you have to calculate, and you can design your riser according to whatever the rule you want to see. But in case of generally shape factor method we use when we talk about appendage in the casting. Okay, in that case you will not be able to easily calculate your casting, your riser design with the help of Keynes method or modulus method. It will be a little bit difficult, but with the help of shape factor method you can calculate the riser design when there are appendage in your castings. Okay, so coming to next question, find the dimension of cylindrical side riser used for casting brass cube of 20 centimeter dimension, volume shrinkage is 9%. Okay, so we have a cube casting with these dimensions, and we have given a volume shrinkage of 9%. So you have to calculate the volume cylindrical, you have to calculate the dimensions of cylindrical riser. One thing here it is not given, that what amount of what will be the amount of your riser according to your volume shrinkage. So we can consider around 3x volume of riser according to your volume shrinkage. So you can calculate that, try to solve it. Okay, so anyone got the answer? Okay, here we can just go with the find the dimension of a cylindrical side riser used for casting brass cube work. So we can calculate the volume of our riser by using this formula, that will be 0.09 of volume of casting into 3 times of what we're talking about. We have to avoid this shrinkage. We will go with 3 times of volume of liquid in our riser. So okay, so we can easily calculate that. Now coming to next question. Find the riser volume to feed a
Can you show
bushing.
previous?
Okay. Uh, okay. So you want to solve me this one? Hello?
No, no, sir.
Yeah, this one.
No, sir. You can continue.
Okay. Okay. Coming to next question. Find the riser volume necessary to feed a bushing with with outer diameter 12 inch and inner diameter 4 inch and height 12 inch. So that will be like this. First, we will make the drawing of the casting which are we are going to make. So we are talking about a inner dia of 4 inches and outer dia is 12 inch and height is 12 inch. So we have to design a riser volume necessary to feed this bushing. So try to solve it with the help of your you can go with the safe factor method. So when we consider safe factor in this type of castings, so we have to consider this core diameter and correction factor also. So when we talk about safe factor, the safe factor equal to L plus W by T. So the thickness will be your true thickness is. So first we will calculate the true thickness of the casting. So that will be 12 minus 4 divided by 2. So that is 4 inch. But when we are going to calculate the, okay, yeah, and core diameter is equal to your true thickness. Okay, that core diameter whatever we have got is equal to your true thickness. So your factor will be, correction factor will be 1.14. Okay, so now the next t will become as 4. So the whatever the thickness you are going to take, it will become 4 into 1.4, that is going to be 4.56 inch. So according to that you will calculate your shape factor, and it will be L plus W by T, and L here we have got length is 12 inches, and W we have to calculate the angular width. So that will come around 8 pi upon 4.56, and after calculating this we will get a value of around 8.14. So we have got a safe factor of 8.14, and with the help of this diagram for 8.14, for creating a sound casting we have to go with a value of around this much. We have to go a value of around zero point 0.6. Okay, for sound, for creating a sound casting we can go with a value of zero point 0.6. So your VR, volume of riser to volume of casting, will be 0 0.6. So we can calculate the volume of riser as 0 0.6 into VC, and volume of casting. Okay, so according to this you can design your, and volume of casting is coming around, after solving the whole thing it will come around 1206 inch cube. Okay, so volume of riser will be zero point 0.6 times of this volume of casting. After that you can easily calculate the riser, just you have to calculate the riser volume. Okay, there is no need to calculate the diameter of or height of your riser. If you want to calculate the height and diameter of riser also, you can consider it as d equal to h. Okay, diameter equal to height, so you can easily calculate the diameter to height ratio of your riser. Coming to next question, determine the dimension of an optim. So any doubt on this?
No, sir.
Okay, so coming to next question, determine the dimensions of an optimum cylindrical riser, height equal to diameter, attached to the side of a steel plate casting of diameter 25 by 12.5 by 5 centimeter by modulus method. So we have to calculate the dimension of an optimum cylindrical riser having d by h. So try to solve it. Okay, so anyone got the answer?
No, not.
Okay.
Yes, sir, I got it. 5.63 centimeter.
Okay, 5.63 centimeter. Okay. So what we have to do in this, we just have to calculate our safe factor first. So the safe factor will be 25 plus 12.5 divided by 5. In sorry, we are talking about modulus method. So we just have to consider one thing. We have to calculate the modulus of your casting. So that will be your volume of casting divided by area of casting, and then you have to calculate the modulus of your riser, that will be volume of riser upon area of riser. And after that you can consider this thing, your uh, modulus of riser should always be 1.2 times of modulus of your casting. So according to that you can calculate the your optimum cylindrical design. Okay, so here we will end our session. So if you have any doubt you can ask. So any doubt if you want to ask.
No, sir.
Okay, so we will end our session. We will meet next Sunday again. Okay, thank you for joining.
Okay, sir. Thank you.